All right, guys. So far what we've been doing is we've been exploring a little bit more in detail some of the properties of capacitors. There's one last property fundamental to capacitors that we need to discuss. This time around, I'm actually going to save it towards the very end because it's going to be a very short video. So this is a fundamental property of capacitors. The first question that I want to ask is, can energy change discontinuously? Right. And the way we're actually going to answer this is I want to remind you of the definition of power. So recall power. Power, by definition, is the time rate of change of the energy, or in the language of calculus, it's dW dt. And the question, formally, is can we have a discontinuous change in the energy in the capacitor? In other words, graphically, let's explain this. Suppose that we were to graph across the capacitor its the energy stored versus time. So here we have energy, probably measured in joules, here time probably in seconds. And this energy might look any curve whatsoever. And then all of a sudden, at some other time here, can it actually jump from one value to another without going through all the values in between? Well, notice that this is not possible. And the reason this is not possible, right, is because for this to happen, the time rate of change of this energy would have to be discontinuous. It would have to be infinite, right? So this right here, this discontinuity would mean that the power, which is this time derivative, this would not exist. It would be infinite. Now, based on physical considerations, it should be clear that you cannot have an infinite power. Right? You cannot have either the capacitor generating an infinite amount of power or accepting an infinite amount of power. What this tells us, as a consequence, a conclusion, and this is the conclusion, is that W, the energy stored by the capacitor, must, and this is one of the reasons why I'm placing this in capitals, I'll even underline it and highlight it, must be continuous. Otherwise, you end up with infinite powers. What we found that for a capacitor, the energy stored in the capacitor is equal to 1/2 CV squared. Now, if this is continuous, and this is a constant, then it must be true that this squared must be continuous too. So if you have a continuous function on one side, it's equal to a constant or two constants times another function, those both must be continuous. So this implies that v squared must be continuous. And lastly, the square root of v squared must be continuous too. V across a capacitor might change as a function of time, must be continuous. That means that if you actually see the voltage across a capacitor, let's say it goes from 1 volt to 2 volts, it must have gone through all the values in between, right? it could not have jumped from one value to another value discontinuously. Right? And that's one of the most fundamental properties of passive. It's important enough here. The circle, we will be using this quite extensively when we take a look at differential equations.